Hey everyone, and welcome back for another deep dive. Today we're going to be tackling something that I always find really fascinating.
Oh, yeah.
Yeah, the way light bends and kind of plays tricks on us.
Yeah.
It's called diffraction.
Diffraction. It's pretty wild.
It is wild. It is wild. And, we usually think of light just traveling, in straight lines.
Yeah, it makes sense.
But when it hits an obstacle, it can scatter and create some really unexpected patterns.
It does, and that's what we'll be looking at today.
Right. Like, remember back in high school physics?
Yeah.
Shining a laser through a tiny slit?
Oh, yeah, I remember that.
We're revisiting that today, but going way beyond.
Well, beyond the textbook?
Yes, way beyond the textbook.
Yeah.
And,
Well, we have an incredible resource for that.
oh, yeah?
Yeah, this website called Open Educational Resources, Open Source Physics at Singapore.
Okay.
And they've got interactive simulations that let you tweak different parameters and see how these diffraction patterns change in real time.
Oh, that's amazing.
Yeah, so that'll help us visualize everything we're talking about.
Awesome.
Yeah.
So let's start with that single slit scenario.
Okay, single slit.
You'd think if you shine light through a tiny opening, you just see a bright spot the same size on the other side.
Right, you'd think that. Light travels in a straight line,
Exactly.
but light has a few surprises up its sleeve.
Okay, I like it. I like it. Few surprises. Tell me more.
Well, you see, light behaves like a wave.
Okay.
And waves,
They love to spread out.
they do spread out. It's like dropping a pebble in a pond. Those ripples don't just stay in a straight line.
Exactly.
They spread in all directions.
Exactly. And that's spreading out.
That's spreading.
That's what we call diffraction.
diffraction. Okay.
And it creates a pattern on the screen behind the slit.
Okay.
It's a bright central band with dimmer bands fading out on either side.
So it's not just a single spot of light.
Nope.
Okay. But why those dimmer bands then? What's going on there?
Good question. Those bands, or minima as they're called, yeah, they're actually areas where the light waves are canceling each other out.
You see, when waves meet out of phase, with a peak meeting a trough, they interfere destructively.
Destructive interference. So darkness results.
Yes.
Whoa. So light can actually cancel out light. That's mind-boggling.
It is pretty wild.
It's like those noise-canceling headphones, but for light waves.
Exactly. And the location of those dark bands,
Yeah.
that's determined by a formula
Okay.
that relates the slit width and the wavelength of the light.
Okay.
The smaller the slit or the longer the wavelength, the more spread out the diffraction pattern becomes.
Interesting. So wait, does that mean different colors of light would diffract differently?
Absolutely.
Yeah.
Because different colors of light have different wavelengths.
Oh, right.
Yeah, so red light, for example, has a longer wavelength than blue light.
Longer wavelength. Okay.
Yeah, so if you were to shine red light through the slit, those dark bands would be further apart than if you used blue light.
Oh, that's so cool. So it's like the slit is acting like a prism, splitting the light up based on its wavelength. But I'm still wrapping my head around this idea that light can cancel itself out. Yeah.
How does that even work?
It's kind of strange to think about.
Yeah, it is strange.
Imagine two waves meeting, one with a peak and one with a trough.
Okay.
If those peaks and troughs line up perfectly, they add together and you get a bigger wave.
Oh, so that's constructive interference.
Yeah, exactly.
Okay.
But if the peak of one wave meets the trough of another wave,
Yeah.
they cancel each other out.
Okay.
And that's destructive interference. And that's what's happening in those dark bands.
Of the diffraction pattern. So it's not that the light is disappearing.
Right.
It's just being redirected or canceled out depending on how the waves interact.
Exactly.
But let's go back to those formulas for a second.
Okay, back to the formulas.
You said the position of the dark bands depends on the slit width and the wavelength.
Yeah, that's right.
What happens if we change those things?
Good question.
Like, what if we start with the slit width?
Slit width. Okay.
Imagine you make the slit narrower.
Okay, making narrower.
What do you think would happen to the diffraction pattern? Well, what do you think would happen?
Well, if the waves have less space to pass through,
Yeah, less space.
I'd guess they would spread out even more.
You got it.
Okay.
The narrower the slit,
Narrower the slit.
the wider the diffraction pattern.
Okay.
It's kind of like squeezing a tube of toothpaste.
Yeah,
The more you squeeze, the wider the paste spreads out.
that's a great analogy.
Yeah.
Okay, that makes sense. So what about changing the wavelength then?
Changing the wavelength. Okay.
We talked about red and blue light,
Yeah.
but what if we use something with a really long wavelength,
Okay.
like radio waves?
Radio waves. Now you're thinking.
Yeah.
Yeah. Radio waves have wavelengths that can be meters or even kilometers long.
Wow.
So if you tried to pass a radio wave through our tiny slit,
Mm-hmm.
it would diffract so much you wouldn't even see a clear pattern.
Really?
It would just spread out in all directions.
So the size of the slit and the wavelength of the wave are both crucial
Very crucial.
in determining how much diffraction occurs. And this is happening all around us, right?
Oh, yeah.
It's not just a lab experiment.
All the time.
Yeah, like how,
Well, think about how you squint to see something better.
oh, like when I'm trying to read a sign in the distance.
Exactly. When you squint, you're effectively narrowing the slits of your pupils,
Oh, interesting.
and that increases the diffraction of the light entering your eyes.
Wait, so squinting actually makes light diffract more, but doesn't that make things blurrier?
You would think so, but not necessarily.
Oh, okay.
You see, diffraction can also have a focusing effect.
Ah.
By narrowing your pupils, you're creating a single slit that can actually sharpen the image on your retina, particularly for objects at a distance.
So diffraction isn't just about spreading light out. It can also be used to focus it.
Yeah.
That's amazing.
Hmm.
It's like our eyes are using physics to help us see better.
It really is a perfect example of how a seemingly simple phenomenon like diffraction can play a crucial role in our everyday lives.
Yeah.
But things get even more interesting when we move from a single slit to two slits.
Oh, double the slits, double the fun, right?
That's right. That's where we start to see the truly mind-blowing effects of wave interference.
Okay, wave interference. Let's
Yeah.
dive into that next.
It sounds good. Get ready for some truly spectacular patterns and a deeper understanding of how light behaves.
I am ready. Let's go. All right, so two slits, two beams of light.
Yeah.
What happens now?
Now we're not just dealing with diffraction from each slit.
Okay.
We're also introducing the concept of interference.
Interference, like two people talking over each other.
Sort of. Imagine it like this.
Okay.
When two waves meet crest to crest, they amplify each other.
Okay.
And that creates a brighter area.
Makes sense.
But when a crest meets a trough, they cancel each other out.
Oh.
And that results in a dark spot.
So like a dance of light waves.
Yeah, like a dance.
With bright spots where they're in sync and dark spots where they clash.
Exactly. And that's what creates that iconic double-slit interference pattern.
Okay.
You get alternating bright and dark bands that are much more defined and dramatic than that single slit pattern.
Yeah. I'm picturing those classic physics diagrams.
Yeah, with the fringes.
Yeah, with the bright and dark fringes. But what determines the spacing of those fringes?
That spacing is determined by the distance between the two slits.
Yep.
And once again, the wavelength of the light.
The wavelength of the light.
The closer the slits, or the longer the wavelength, the wider the spacing between the fringes.
So just like with a single slit, changing the wavelength of light would change the whole pattern.
Absolutely. It's like tuning a musical instrument.
Okay.
By changing the wavelength, you're changing the tune of the interference pattern.
I like that.
Yeah.
Okay, that makes sense. But here's something I'm wondering.
Yeah, what's that?
We've got diffraction happening at each individual slit.
Right.
And we've got interference happening between the waves from the two slits.
Mm-hmm.
How do those two things work together?
That's a great question. What we see in the double slit experiment is a combination of both phenomena.
Yeah.
The diffraction from each slit.
Huh?
That determines the overall spread of the pattern,
Okay.
while the interference between the two waves,
Yeah.
that creates the specific bright and dark fringes.
Within that spread. So they're not competing with each other.
No.
They're working together to create this complex pattern.
Yeah, working together.
It's like a symphony with different instruments all playing their parts
Oh, I like that.
to create a beautiful, harmonious sound.
Yeah, a symphony of light waves.
Yeah. And speaking of symphonies,
Yeah.
things get even more intricate and magnificent when we add more slits.
More slits?
Yeah, like a whole orchestra of light waves.
Okay, tell me more.
What happens then?
Okay, so imagine hundreds or even thousands of slits
Wow.
etched closely together. This is what we call a diffraction grating.
A diffraction grating.
Yes.
So instead of two sources of light, we now have a whole army of them,
Which-
each interfering with each other. What does that do to the pattern?
Well, it takes the interference pattern to a whole new level.
Okay.
With more slits, those bright spots become sharper and more intense,
Okay.
and the overall pattern becomes much more defined and complex.
It's like upgrading from a standard definition TV to like a 4K ultra high definition TV.
Exact.
Everything just becomes crisper and more detailed.
It does, and this ability to create such sharp and precise patterns has incredible applications in all sorts of scientific instruments.
Wait, so we're not just talking about pretty patterns anymore.
Nope.
This has real world uses.
Oh, yeah, for sure.
Okay, like what?
Well, one of the most common applications is in spectroscopy.
Spectroscopy.
Yeah, where scientists use diffraction gratings to analyze the light emitted or absorbed by different materials.
So you can shine light through a sample.
Yeah, through a sample.
And the diffraction grating would help you figure out what's in it.
Precisely. Every element or molecule has its own unique spectral signature. So by separating light into its different wavelengths using a diffraction grating, scientists can identify the components of a sample,
Okay.
whether it's a distant star
Wow.
or a drop of blood.
So diffraction gratings are like light detectives.
Yeah, like light detective.
Helping us uncover the secrets hidden within light.
That's a great way to put it. And their applications go far beyond just chemistry and physics.
Oh, really? Tell me more.
All right, well, let's zoom out a bit
Okay.
and talk about telescopes.
Okay. Telescope.
Diffraction gratings are essential components in many modern telescopes,
Okay.
helping astronomers study the universe in unprecedented detail.
So these gratings are helping us see things that are light years away.
Exactly. Remember, the sharper the diffraction pattern,
Yeah.
the more precisely we can separate and analyze the light.
Okay.
And in telescopes, diffraction gratings help to improve resolution,
Okay.
allowing us to distinguish between closely spaced stars or to see fine details on the surface of planets.
It's like giving our telescopes a super-powered vision boost,
Yeah, a super-powered vision boost.
letting us see things that would otherwise be blurry or completely invisible.
It's a powerful tool for exploring the vastness of space.
It really is.
And it all stems from the simple principle of diffraction.
This is incredible. We've gone from a single slit to a symphony of light waves, and now we're talking about seeing distant galaxies.
Yeah, it's pretty amazing.
It's amazing to think that something as simple as the bending of light can have such profound implications.
It really is.
But you mentioned that diffraction isn't just about stars and telescopes.
Right.
What else is it used for?
Well, let's bring it back down to Earth for a moment.
Okay, back Earth.
Have you ever wondered how CDs and DVDs store so much information in such a small space?
Yeah, actually I have. I mean, those shiny discs hold entire movies and albums.
do.
How does that even work?
It's all thanks to diffraction and interference.
Okay.
The information on a CD or DVD,
Uh-huh.
it's encoded in a series of tiny pits,
Tiny pits.
arranged in a spiral track.
Okay.
When a laser beam shines on the disc. Yeah.
The light diffracts off these pits,
Right.
creating a unique interference pattern.
Wait, so those tiny pits are like miniature diffraction gratings?
Exactly.
Wow.
And by analyzing the subtle variations in the reflected light, a sensor in the CD or DVD player can decode the information stored in those pits.
So it's like a secret language written in light.
Yeah, secret language written in light.
And it's all thanks to diffraction.
Precisely. The precision with which we can create and read these diffraction patterns
Yeah.
is what allows us to store vast amounts of data on these compact discs.
I'm starting to realize that diffraction is much more than just a physics phenomenon.
Yeah.
It's a fundamental principle.
It's
Woven into the fabric of technology, communication, and even our understanding of the universe.
It's everywhere once you start to see it.
It really is.
And it all comes back to that simple but profound idea.
What's that?
Light behaves like a wave.
This has been an incredible journey so far.
It has. We started with a single slit and ended up exploring the vastness of space and the magic of CDs and DVDs.
Yeah.
But something tells me there's even more to this story.
Oh, there's always more.
What else can you tell us about the deeper implications of diffraction? So we've covered a lot of ground,
We have.
from squinting to see better to those mind-blowing holograms.
It's pretty amazing stuff.
It's incredible how something as simple as diffraction can have such far-reaching implications.
It is. It really highlights the interconnectedness of everything.
It does.
But, all this talk of diffraction and interference, it actually brings us to one of the biggest mysteries in physics,
Oh.
the wave-particle duality of light.
Oh, yeah, the whole is it a wave or a particle debate.
Yeah, that one.
I remember scratching my head a lot over that back in school.
Yeah, it's a tough one.
It's like light can't make up its mind.
It can't decide.
Yeah.
It's one of those concepts that really challenges our everyday intuition.
Yeah, because we tend to think of things as being either waves or particles.
Right, you're either one or the other.
But
Light's different.
light's different.
It plays by its own rules.
So how does diffraction fit into all of this?
Well, that's the interesting part.
Okay.
Diffraction experiments,
Right.
like the double-slit experiment we talked about,
Yeah.
those were actually some of the first pieces of evidence that light could behave like a wave.
Really? So diffraction helped to change the way we understand light at a fundamental level.
It did. For centuries, scientists believed that light was made up of tiny particles
Okay.
called corpuscles.
Corpuscles, okay.
But then along came diffraction.
Diffraction's like, hold on a second.
Yeah, there's more to this.
There's more to light than you think.
Exactly.
Yeah.
Showing that light could bend and interfere with itself.
Okay.
Like waves in water.
So that realization led to the development of quantum mechanics.
It did.
Oh, quantum mechanics. A whole new branch of physics.
Yeah. Now that's a rabbit hole I'm always fascinated by.
Oh, it's a good one. Where things start to get really weird and counterintuitive.
It can be mind-bending for sure.
Yeah.
But at its heart, quantum mechanics acknowledges that light.
Yeah.
And indeed, all matter has both wave-like and particle-like properties.
So it's not that light is one or the other.
Right.
It's both at the same time.
Yeah, both at the same time.
How is that even possible?
That is the million-dollar question.
Yeah.
It's a concept that's still being explored and debated by physicists today.
Wow.
But diffraction provides a tangible way to observe this duality in action.
Okay, I'm intrigued. Walk me through this. How does diffraction show both sides of light?
Okay. Think back to that double-slit experiment.
The double slit, okay.
When you shine a beam of light through those two slits,
Yeah.
it creates an interference pattern, right?
Right, that's a clear indication of its wave nature.
Exactly.
Yeah, the waves are interacting with each other, creating those bright and dark fringes.
Right. But here's where it gets interesting.
Okay.
If you dim the light source enough so that only one photon, a single particle of light,
A single photon.
is passing through the slits at a time,
Okay.
what do you think happens?
Well, if it's just one particle,
Yeah.
shouldn't it just go through one slit or the other?
You'd think so.
Yeah, no interference, just two bright spots.
That's what you'd expect.
Yeah.
Based on our everyday understanding of particles.
Right.
But that's not what happens.
Really?
Over time, as individual photons pass through the slits one by one,
Yeah.
they still build up an interference pattern.
Wait, what? So even though they're acting like individual particles, they're still somehow interfering with each other?
They are. It's as if each photon is passing through both slits simultaneously and interfering with itself.
So a single particle of light can be in two places at once.
That's the essence of wave-particle duality.
That is seriously mind-blowing.
It really is.
So diffraction experiments like this provide a window into this bizarre and fascinating quantum realm.
They do.
It's like those photons are playing a cosmic game of hide and seek,
Yeah, high and seek.
defying our expectations and showing us that reality is far stranger than we could ever imagine.
I love that. That's a great way to put it.
So diffraction isn't just about pretty patterns and cool technologies.
Nope.
It's a gateway to understanding the fundamental nature of reality itself.
It really is. And that's what I find so compelling about physics.
Yeah.
It's this constant journey of exploration, pushing the boundaries of what we know and challenging us to think differently about the universe and our place within it.
This deep dive has been a perfect example of that.
It has been a good one.
We started with simple questions about how light bends and ended up exploring the wave-particle duality of light and the mind-boggling world of quantum mechanics.
And we did it all thanks to diffraction.
Diffraction. Well, I think we've all learned a lot today.
Me too.
And it's a reminder that there's always more to learn,
Oh, yeah.
more to explore,
Yeah.
and more to wonder about.
Absolutely.
And I, for one, can't wait to see what other mysteries the universe has in store for us.
Me neither. Who knows what we might uncover next?
Exactly. Well, thanks for joining us on this deep dive into the fascinating world of diffraction.
Yeah. Thanks for listening.
Until next time, keep those curious minds engaged and never stop exploring the wonders of the universe.